Okay, hello everyone, and let's continue with our course Embedded Systems. And today lecture will be about the control, but we'll have quite different control that we had on the previous lecture. On the previous lecture, we had it's most related to the functional control or control by transfer function or control function. In this course, we will have control with a behavioral control. We will control not as in the previous lecture that was related to keep a parameter on a specific level. Today, we will control or we will discuss about how to control the behavior of the system. Yeah, behavior of the system also taking into account the physical changes on the physical environment. Okay, so we will continue with finite state machine control. Okay, so first let's discuss about the finite state machine. What is a finite state machine? Finite state machine, as a definition, it is an abstraction that describes or provide a solution for a problem. Okay, by definition or by defining the behavior of the system in the format of a machine mechanism that change from one state to another as a response to some physical environment changes or following some changes on the input signals, and of course it's providing a specific output as an reaction to the physical changes and the internal state. Okay, anyway, the finite state machine control provide as a system, it's following some inputs. Okay, it's following some inputs and is providing, evaluate that and provide specific outputs according to the output definition function. So why we have finite state machine? Let's discuss about the state. What is a state? A state is let's say a shape or is the state in which the system is at the moment. Let's give some examples for state. Me as a person, I'm in the state of sitting or stand up or doing something. Yes, but this is a continuous state in what I'm in. Same for the devices, but in comparing to me, I can be in an infinite type of states. Let's say I'm staying like this, after that like this, and I'm changing a lot of various kind of states that I can define. Okay, this is the state number one, state number two, and so on. For finite state machine, that means all those states are well defined, and it is a finite number of states. Let's say that we have a car. We have a car, and let's define the states on which this car can be on a specific moment. It could be on a initial state or an idle state, meaning that it's staying in the parking state, okay, and switched off. That means, okay, we are in the idle state, or most probably we are in the parking state. Okay, the parking state is the moment when it is staying with parking brake activated. Okay, we can have another state that acceleration, when we just kick off or starting driving. The other state could be the state when it is driving. or braking is another state. Okay, we have a finite number of states in which a car can be at a certain moment. Okay, now a finite state machine is defined by the finite number of states where the one of them is defined as the initial. We have the finite number of system entries or system inputs. Yeah. Why? Because me as a person or as a human, I can see a lot, or I even can say that I can see an infinite number of inputs. Yeah, because I can look into one point, another point, and make a decision of an infinite number of stimuli. Why? Because this is me. This is how we see the environment. We can generate even what kind of input we should follow. Yeah? For the system, the internal function will look after a finite number of inputs. Okay, such inputs could be what? Inputs from the sensor, inputs from the user interaction. Now, if we are defining that the system has as the input some sensor, okay, of course we will have a finite number of sensors, okay, or finite number of input entries. That means we have keyboard will be one entry, one sensor, the temperature sensor will be another entry, and humidity another entry. We'll have three entries or others, but the number will be anyway finite one. Okay, finite number of generated outputs. Okay, we can generate what? For a car, let's say we have to generate the lights, yeah, some driving wheels, direction. We have three outputs, three generated outputs, or 4, 5, but the number will be a finite one. Okay, the state machine will have two main functions. One is the definition of the function for the output, that is dependent on the internal state or input states, but we will define how we provide the output. And of course, the transfer function, that is defining the way how the finite state machine changes its own internal states. Okay, let's go further then and go deeper inside a finite state machine. Most probably you already met such diagrams. Okay, just provide me with an feedback. Did you ever seen such diagrams, or on the first, okay, put by a dash. Okay, did you ever, first question is, did you ever seen such diagram? And second question will be, did you ever use such diagram, finite state machine diagram? Okay, I'm waiting for your answers. Yes, okay, put by dash. Okay, first, second question, first answer and second answer. Yes and no. Thank you. Others? Did you ever use such diagram? Please, two answer. Yes, no, no, yes, 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 different values. Okay, usually the finite state machine is not related only to the embedded system. Okay, today we will discuss about in general about the finite state machine, but the application will be related to embedded systems. Yeah, why? Because the source of the information will be the environment, and the action we are providing will be also the environment. So we just will follow some inputs and provide or generate some outputs. Anyway, a finite state machine is a model of behavior that is made or composed of states, transitions from one state to another, and some actions Let's say that we have such diagram when that is defining the behavior of a door. Okay, and we have the state open, opening, okay, and close, and open and close, and those two states we will have two, we will provide two outputs. In the close and open state will continuously opening, okay, but depending of course of the input that we are reaching the limit of the door. Let's say that this is the diagram of state machine for the market entrance, automatic open close, and so we will have two transitions: switch to open, okay, button to open, in our case will be the sensor, and button for the transition from the close to open, and transition from the open to close. How it will be? We will have a sensor of the presence, and the condition to go from one sensor to another will be the 0 to 1. Okay, one will detect 1. That means we have to go from open, from the close to open, and in case we will detect that is 0 for, I don't know, a specific period of time, we'll have to transfer here. This is how the how an finite state machine is behaving. Okay, so an state machine is defined by a state that usually store information about the past, and a good example is this one. And meanwhile, I would like to have some inputs from your side about what do you think about this diagram, what it is defining, or the behavior of what kind of system it could define. So please provide me some ideas. Okay. Meanwhile, I will discuss, or I will say some, I'll make some comments about what are the components of finite state machine. So feedbacks meanwhile. Okay, so a state store information about the past. What that means, that in one specific state we could reach only going through some previous states. That means, let's say at the top we can reach only by going through the going up, okay, via idle, via bottom, okay, but anyway we can reach at the top by this way. We'll have or this history of the states of the changing, but of course it is not just we can say that okay, the current state will be this. No, it will have an evolution until reaching the specific states. Second, a transition. A transition indicates of a change. Let's say top limit hit, yeah, or go up button. We have to check something, okay, a condition. Do we have the button pressed going up, or did it reach the upper limit? Okay, and those are conditions. And a transition usually indicate the way, or what is the condition for changing the state, let's say from the idle to the going up, or from the going up at the top. Yeah, so transition is the changing state according to or by satisfying a specific condition. And the last one, an action. What is an action? The action is how the system is behaving in a specific state. Okay, when I'm the state going up, what is the behavior? Switching on the motor, or most probably in this state, we will check the sensor for top limit hit on various behaviors. So the system could be defined by specific states, action or behavior on a specific state, and some transitions between states. So still waiting for feedback. What do you think about this diagram? What it could define? Okay, yes, it is an elevator, but in other courses I had some feedbacks like it could be a drone, it could be an let's say submarine, because we don't have a specific one, but we have what here? We have upper limit, okay, or let's say we want to raise the drone to a specific value. That means we got the upper limit. Same for elevator, we have a sensor of upper limit, and for a drone, okay, we have the altitude. Yeah, and we have here what? Top limit, bottom limit, and we have here, let's see, we are first time we are in the idle state. I don't know, but when I'm going or I'm entering an elevator or a lift, okay, what I'm doing, I'm pressing the button going up or going down, doesn't matter on which stages stair on which floor I am, but I'm pressing the button. Of course, if I'm on the bottom floor, it is possible to press the button go down, but we'll see what will be the behavior according to this diagram. Okay, so when I'm in the idle, just started the switching on the elevator. We are entering in the initial state. Remember, we discussed that the finite state machine has a lot of many states, but one of them is the initial. In our case, we have the initial state, the idle state. We say, okay, we have a variable that is a specific variable for the states, and we say, okay, the initial state or the starting on the setup, we will define it, okay, the state is equal to idle. Okay, now when we sense the button go up, it will change the state from the idle to going up. So the action in going up will be switch on the motor to elevate us or to lift up the cabin. Yeah. So here the motor will be on and will stay here until what? Until we will satisfy the condition top limit hit. Okay, when we will have the top limit hit, we will transfer from the state going up to at the top, and what will be the action at the top? Stop the motor and activate the brake. We'll have to activate the brake in order to not slide down. Yeah. So now we are on the top. Okay, the door are opened. Most probably we'll implement another finite state machine in the finite state machine. Okay, opening the door and at the top. Yeah, but when entering in the lift, again at the top we are pushing go down. Yeah, and we will transfer to going down. So brake will be released and the motor will slide us down until the bottom limit hit. So at the bottom limit, stop the motor and again activate the brakes. So we'll have brakes activated. Okay, and now on the any moment on going up and going down, we have the possibility to halt. In this case, we are pressing the emergency stop button, and on the emergency stop button press, we'll go to the idle. That means stop the motor and have the brake activated, or depends of the what is the behavior on the emergency, but we will stay on the idle state. And from this point we can go. Let's imagine we stopped between the floors. In this case we can go back, up, or down. And let's imagine this is not an elevator or a lift between two floors, but is to lift us on top of the building and down of the building. Yeah, or an elevator for window cleaning. Yeah, in this case they will have will need the opportunity or possibility to let's say rise the elevator and slide down, go down at the specific moment. And in this case we'll have some changes here, but the top limit and bottom limit are more for protection. Depends on the problem definition. For the automatic elevator will work only here, yeah, or between floors. But when we want manual control, we'll have a behavior between those three states. Let's see, this is a generic state machine for an elevator. Okay, maybe here could be a top limit or a set point for the floor. It's also an option. Okay, so this is one of the simplest state machine implementation. This is a regular one, but we can have a very complex state machine design. Let's say that we have a lot of transition control, and even let's say all by all connected, and we will have to define what are the actions for every state, what are the states, what are the action of the states, and what are the conditions for transition between states. Yeah. So this is how what are the terms with which we are working when we would like to control or define a control system by defining the behavior. But of course we can mix finally, but this is the basics. So let's discuss or try to see at the implementation state what we have. Okay, and from the implementation point of view, we can have two types of finite state machine. Okay, we can have a type of Moore state machine or Mealy state machine. What is the difference between them? The difference between them is that one of them we can say that is a delay state machine. That what that means? That means that any changes from the input can be applied to the output only after state change. What that means? First, we have a transfer logic or transfer function for the state that is depending only on the current state and input, and we change the state memory or the state variable. Okay, we have a function for changing the state. State one, okay, going up, going down, opening, closing, and doesn't matter what, but according to our state machine design, we decided that we will have this finite number of the states. Okay, and now for changing state, we have a transfer logic or a transfer function or a transition logic that is changing states depending of the sensing, or I don't know what kind of input we are using for that. And the output is depending only on the state. And this kind of finite state machine has the name Moore machine, or state machine with delayed reaction on the input. Why delayed? Because first of all, we have to change the state, and only after changing the state we can provide an output. Okay, another kind is milli machine state machine. Yeah, and the milli state machine, the only difference is that the output is depending on the current state and on the input, so it can react immediately on the input change. For the state memory or state change, we use also a transfer function. Okay, it's not the same. Every state machine is a specific and it should be designed from scratch according to the system requirements. The difference between other systems and finite state machine is defining a behavior, and when we define or change the behavior of a system, even a small change, we should redesign the whole diagram. We cannot just scale it, one sensor, many sensors. Okay, we cannot say one state, many state. No, every change should be defined, because in case we are adding one specific another or a new state, we have to define from which state we can make a transition to this state, and on what states this we can go from the new states. And in this case we should define it from the scratch, and what output it will provide. Will it be dependent on the input or not? And in case the output of the system is dependent on the input directly, yeah, let's say y is equal to f depending on the input on the state. So in this case, we'll have an immediate state machine. So we'll have delayed state machine and immediate state machine. The difference between them is is the output dependent on the input directly, or it is dependent only on the state. Okay, but anyway, the state is dependent of the input. Now, when we are defining the state machine, we'll have quite different design approach, because for the Moore machine, we will define states and y's outputs according to the states. Yeah, and everything will define inside of the states here. Okay, and in those diagrams we will have xn are the inputs, yeah, yn are the outputs, and sn are the states. So we have state 1, state 2, and in state 1 we are providing with the y1 output. In the state S2 we are providing y2 output. And now changing between state 1 and state 2, and only the state 1 and state 2 is depending on the x1 being the transfer condition in our case. Yeah, and it is depending only on of the x1. Staying here is depending on x2. Transfer back to the S1 is depending on x3. This is the condition. And in case of x4, we have this transfer. The S1 is the initial state. First, we are going here, and when we have a change on an input x1, will transfer from here to here. When we'll have x2, we'll go here, and the transfer from here to here is not depending on x3. You see, only by x1 is, this is the condition. Now, going to the milli-state machine or immediate state machine will have states separately, okay, and the condition of transferring states are x1 and x3 and the same. Yeah, we see that transfer of the it's not changing, is depending on x1, but the outputs are defining dependent of the x1, and this is the design approach for the milli-state machine. Because look, on the state 1 we can generate two types of y. When we have transition x2, we are providing x y2. When we have transition y3, we'll have y3, x3 will have y3. And now after changing here, we'll change the outputs, but it's depending on the state and depending on the transition. So the y, the difference between y to generate y3 or y2, it depends on state 2 and the input, or state 2 and another input. Yeah. This is the different and the design approach. Now, when we have to use that, let's imagine that here we have a state of 2 bits or two states. That means the output could be always two types of output. Yeah, that means if we have the state number 1, in this case we'll have the output number 1, and we could define the output by just table, a transfer table, or a function plus or something like that. On the output, we can say that, okay, we have the input provided to the output, but it is modified by the current state. Okay, always we have provided it to the output by a function, of course, but it is changed by the current state. It's a kind that we can control the flow when we are controlling the position to control the input or dependency of the output on the input by, let's say, by the pattern. Let's say that we have here in the input a pattern. We are controlling the network data flow, and we always checking the CRC if the pack and the protocol is followed. If the protocol is not followed, then change the state memory to what? To the fail, and don't provide the input to the output. But in the case is everything okay, the input is provided to output. This is just an example, yeah. But we have the direct dependency of the output on the input. In this case, it is not possible. The output is depending only on the state. Okay, but this is what we have. And in case of outputs are depending on the input, in this case we have various states of the input, and in this case we have the same changing of the output. Okay, now at this moment, please provide me with some feedback if you understood the idea of what a state machine means. Waiting. Yes, from 0 to 5, and provide the answer to everybody, not only for me. Others, please. Waiting. Okay, thank you. Others, please, because I want to see how you understand and maybe go deeper. So the general idea that we should provide some behavior by changing from one state to another. This is the main principle. Okay, and on every state, the system is we are behave or provide a specific output. Let's say that we depending on the state, we are going to control by specific parameters for PID control, and on another state we are going to provide another, yeah, and be changing the states, and on difference on the various states we are provide different actions, yeah. And now we have just to define how we transfer from one state to another, yeah. Let's say we change the parameters for the PID. If we are going, we detect that we go go upper than one than a threshold, yeah. And in this case, if we are higher than threshold, we change the PID parameters, and we in this case will have a state machine control of an PID, and we will have combined control, PID control for the output control, yeah, and finite state machine for control. In this case, we'll have a kind of milli state machine, because the output will be immediated, and here we'll have the PID, but here we'll have the control. This is just an example, but we can define everything. Again, the finite state machine is not related only to it's not related only to the it's not related only to the embedded system. It is widely used for the software engineering even. Okay, so let's go further. So now, how we could define a state machine for an embedded system? So let's think this way. We have a task for Moore finite state machine, and we'll have another task for milli state machine. Okay, for the Moore state machine and milli state machine, and we'll see what is the difference in the implementation. Anyway, we'll have such stages, and we see the stages. By the way, let me correct this here now, because it's a kind of doing so. Yeah, this is the correct way, but I'll explain why. So, sorry, it's in Romanian yet, but let me explain this about state machine. Okay, in the Moore state machine, we have the output dependent only on the state machine for the milli state, current state, and input. And we see here the difference. Yeah, the next state is depending on the input and the current state. Same for the milli. Next state is depending on the input and the current state. Now, here on the Moore, the output is depending only on the current state. For the milli, the output is depending on the input and the current state. So now let's go further. When implementing here the task for Moore, we first of all are evaluating the output only by using the current state after waiting for a delay, okay, for the next recurrency, yeah, for the next recurrency. And when next recurrency occurs, we are collecting again the inputs and change the next state. Collect the output, get, yeah, and so here is something like set outputs, delay, get inputs, and transfer to the next state. So after one recurrency, we'll go again Let's imagine that this is a continuous loop. We'll go again to evaluate the output according to the current state, wait for recurrency, collect inputs, evaluate next state, and so on, so on, so on, always continuously. For the milli, we have an immediate state machine. That means first we are waiting for a while for a recurrency. After, we are collecting the inputs, evaluate the next state, and immediately evaluate the state and that is evaluate the output according to the inputs and the current state. We see the order is the same, yeah, because we have, but it depends when the we have the delay and when we have the evaluation of the output. Now we can of course somehow around, but the difference is this one. The main difference is here we have inputs, here we don't have, we have only current state. But here we have inputs and current state. Okay, when we will define the diagrams, we will use something like this. Here we have the name of the state. Here we have the output. Let's say we generate output 1 to 3 as the value. Yeah, and we will stay in this state for the 30 recurrencies. Yeah. For the millist, and this is the condition that will trigger the transfer from one state to another. Maybe we can have another trigger for the transition. Let's say next if input is true, or another next true if the input is true. Okay, now millist, and for the milli we will use this kind of diagram. The name of the state is go, wait time is here. Let's see, but if the trigger is 1, the output will be 1 to 3 immediately. Yeah, if the input is true, let's say, then the input will be the output will be, let's say, 4, 5, 6 and so on. Okay, if we'll have another transition, let's say. So but this example or diagrams is inspired from the edX courses regarding the embedded system, but it's only the topic for the finite state machine. So I recommend if you think that you can use such approach to your behavior or to the behavior of your PBL project, in this case, maybe is the case to go through this course at least at the finite state machine, because it's very interesting and very informative. Now I will have the same problem or projects I will use inspired from there, but with our own explanation. And let's see how really we could define we could solve problems with such with finite state machines. So the first problem we would like to solve, and let's try to solve it by solving the problem of the LED. And let's imagine we have such, this is the Arduino, let's say, and we connect an button that on pressing the button, we will have here the logical 1, otherwise we'll have the ground here via this resistor, okay, because here on the input 8 is connected to the ground by this resistor. But when pressing the button, in this case, we are providing to the output the power supply, yeah, and the LED is connected via, okay, of course, limiting current resistor to the input 2. Now, let's define for LED, we will have two states, LED on and LED off. So in this case, the LED will switch between, according to our behavior, will switch an on, off, depending on the button press. Now, the behavior should be like this. Pressing the button, it will change to the off, pressing another time on. Okay, so let me play a little. Pressing the button on, pressing the button off, pressing the button on, pressing the button off. Okay, it's a kind of playing with hands, but okay, this is demonstrating by hands, but real engineering consists on defining that by a diagram. Okay, we have two states, LED on the state LED off, where the output action is providing 0 to the output or providing 1 to the output. In order to, this is the action, actually, the output action to this pin. Okay, we have state on and state off, where we are providing logical 0 or logical 1 to this pin. In case of different connection of the LED, most probably be could have a different system. Yeah, let's imagine that we are connected not like this, but the LED we are connected not to the ground, but to the power. In this case, we are controlling the LED by 0 logic. Yeah, and providing 0 logic, it is switching on, and providing 1 logic is switching off. But by these diagram schematics, we have this situation. More than it, even on application, I'm using for the LED different and for button different. But this diagram was built especially to be more related to the 1 logic or 0 logic. So when I have LED off, I provide the 0 to the output. When I have on, I provide 1 to the output, to the physical. Okay. Now, the transition between LED off and LED on, we have on detecting 1 on the button press. So when I'll press the button, the power supply will be applied to this pin, and I will have on the input the logical 1, or electrical signal, logical 1. And when I detect 1, it will change here. If not, then I will change. The next state will be off. Okay, when it is 0, next state for the LED off will be LED off. If I will have at the input, it will have 1, I'll have this transition. So from the LED off, I will have 2 types of transition. From LED off to LED off on detection on the input 0. Yeah, this type of the diagram. Or I'll have the transition LED off to LED on by detecting 1 on the input. So if you remember, we defined it on the first laboratory work. We defined the behavior of the LED by if it is on, then switch it off, and so on, by just a flow chart. This is the case to change a little the design approach by using finite state machine, and you will see that it's more behavior related, and we don't have to check how we implemented it with the follow chart, but we should define what are the state of the system. Okay, we have 2 states of the system. What are the transition conditions? We have 1 press of the button and 2nd press of the button. So in this case, this is the transition. Now, this behavior can be converted to a table. So we have the number. We have the number of the transition and the symbol of the transition, or the name. Yeah. So the LED off will have the ID 0 or number 0. The LED on will have the ID 1. The output provided is 0 for LED off and 1 for LED on. The delay or how much time we have to stay in this state is provided by the delay. Yeah, this one, or let's see here. Yeah, delay. And you'll see the miracle after a few steps, but let's wait a little. And here we'll have two types of transition. We can transfer from the LED off first if we will detect on the input 0. In this case, we are transferring from LED off to LED off. Yes, this is the transition. And from LED off to LED on detection 1, the input. Personally, I will prefer to define it by symbols, but now for learning purpose is okay to have such. But this is button pressed or button released. Those are the inputs. Okay, button pressed and button released. If button is released, then stay in the same state, and here too. Okay. Now, second state on LED on, we have also one transition and the second. So from LED on, we can switch to LED on back. Okay, on detecting 0. LED on. Most probably we will have to define another association here. And the second transition we'll have from LED on to LED off, like this one. Now let's see how we implement this in source code. So we are defining here by define LED off state 1 and LED state 1. Okay, this is number. Personally, I would prefer to define it as an enumeration. Yeah, in this case, I'll have automatically, but better to control the IDs, this ID. So always use symbols, but keep in control. This is one of the main issue. Why? Because we should have a counting number of the state. We don't have to miss some number on the counting of the state. We'll see for the next. Why? Because we will use this ID in order to select it. Okay. Now let's go further. We will define object, in our case structure, for the state, where we will have defined what is the value for the output, what is the delay, and the number of the inputs. Okay, that will affect for that is will select for the what will be the next state. Let's see. And now this next will be how many inputs we are following. And in this case, we have 2 because we have 2 inputs. So next state is depending on 1, 2 inputs. Okay, next set for input 0 and 1. So 2. Defining this as type with the type def. So now we are defining the state machine itself by providing 2 states. Okay, first 2 states, number of states 1 and 2. And now we are providing for every state, we are configuring this structure. So now what we have to do is just to copy paste from the table to this structure. So first output, first term is output. Here we have 0, copy it here. Delay 10 milliseconds. We have 100 milliseconds, but taking in account that we have 10 milliseconds delay units. In this case, we'll have 10 multiplied by 10, and we'll have 100 milliseconds. So we defined the output, we defined the time. Now it's time to define the states, next states. So we'll have here two, according to the two inputs combination. So in this case, we have LED off, yeah, and LED on. For the second state, okay, the state number 1, we'll have the output 1, and we will have delay the same 10 milliseconds, 10 multiplied by 10 milliseconds. Next state for LED1, on the input 0, we'll have LED on, put it here, just copy paste, okay. Here is LED off, copy paste it here, and let's see now. We have first thinking about how it will work, define the behavior by finite state machine diagram, convert it to a table. After that, just by a copy paste, convert it to the source code. Okay, so now let's go to the final implementation. Yeah, here it's a kind of ta-da, this is how it's working. Ta-da! So we will implement it by the Moore finite state machine because we don't have direct dependency of the output to the input from the input. Okay, so in the Arduino, or the laboratory work number, I think is 5, to the control, the first task will be like this. You just can implement as is, but you have to test because I didn't here tested it. So we have what? First of all, we have to define the pin, and we'll see that the pin number 2 is for LED. The button is connected to the 8. Yeah, it's here, 8. Okay. Now we define the state, and the state machine configuration is just the same what is here. Just this is just a part of this implementation. So they have the same. Now, as you remember, we have one of the state is the initial one, okay? When the 1 is defined as initial. In our case, we are defining here initial by starting the system, but anyway, in the setup, always when we define it as the LED off state, yeah, always. Now, we are configuring the LED pin and button pin. Button pin will be as the input. So we need the inputs, we need the outputs, just to configure. Now, ta-da! The implementation will be exactly like here, right? Like here, yeah. First of all, we are evaluating the output, and the output will be collected from the FSM configuration. So it will take the output, okay? This value will be applied here. And as the initial state is off state, initially it will take the off state, yeah, the off state is 0, yeah, off state is 0, so it will collect the first line, yeah, and the first line, the output, yeah, this one, this is 0, and it will continue, and it will always have initially when it will start, always will provide output 0, and it will be applied by the function digital write. So we collect the output, extract the output from the state machine, apply it to the pin. Okay, and now for the next time, we are waiting for the delay, yeah, waiting for the delay here for this period. In our case, we have 100 milliseconds, define it here, yeah, and collect it from here 10 times by 10 milliseconds. 10 times by 10 milliseconds. Okay, for the Arduino, just Arduino implementation, we can do that by the loop. But in the if you'll use sequential or FreeRTOS system, for the FreeRTOS, you'll have to use the task delay function. For the sequential, you'll have to use a specific state in order to let's say to say how many recurrences to skip, kind of a second counter for the delay. Okay, now the third step is collect the inputs. So we are reading the button and see if we can change here the state. And next state will depend on the what we read for the from the button. So if the button will be low, so 0, in this case we'll have directly the 0 state, meaning off. If the button will give us the result 1, in this case we will select it directly the input, the combination 1 from the finite state machine. Why? Because we have the next 2 inputs dependency, and we will, depending on the input, we'll select one or another next state from here. Yeah. So this is the how it will work. So, but you will see that this implementation always will be the same. We even will not change this implementation. Doesn't matter where, how, what will be the configuration of the system machine, finite state machine, because finite state machine configuration is here. So we can copy paste it for every solution, every system finite state machine you will have. Yeah, like here, but you'll have to work on design. So defining the diagram, convert to the table, and fill the table. Yeah, this here is the finite state machine. Number of inputs, finite number of inputs, finite number of states, and we have the transition defined by changing, and the changing will depend, of course, of the input or on the output. So now we have a few minutes. So let's go to the next solution, and we'll see how quite similar is the button press finite state machine to a more complex problem. So let's see how we control a smart traffic light. And let's imagine we have a smart traffic light where we have some sensors that is detecting that if we have a car flow from the east or and car flow from the north. Yeah. And in this case, we should change smartly the traffic lights. And all the system will consist on small microcontroller, let's say an Arduino or something like this, a microcontroller, where we will have 2 pins for the sensors from the north or the east. Yeah, 0 for the east, the pin number 0 for the east, or the bit number 0 for the east, and bit number 1 for the north. And we have another 2 traffic lights with 3 LEDs each that is connected like this. The less significant bits LSB is connected to the green, after that yellow, red for the north direction, and the green, yellow, red for the east direction, where the most significant bit, the 5th, is related to the red of the east direction. So we'll have something like this. Yeah, this is the output and this is the input. So 0, 0 meaning nobody asked for going through the intersection. 1 1 means both are asking for. Now 0 1 0 1 means that east is asking to pass the intersection. 1 0 meaning that only north is asking. Yeah, so we have for the input we have 2 bits, and we will have 4 combinations. 4 combinations. We'll have 0 0, nobody is asking. 0 1, 0 1 is asking for passing. We have here some cars, okay, or only east is asking to pass the intersection. 1 0 1 0, when only north is asking for the to pass the intersection, and 1 1 we see here 1 1 is asking to pass intersection. Okay, 0 0 is 0, 0 1 is 1, 0 2 is 2. We see here, yeah, 0 1 2 3 0 0 0 1 1 0 1 1. That are the combination, and we should take care that we have exactly this combination here. Yeah, so 0 1 2 3, and my previous remarks are to keep it counting 0 1 2 3 and to not have but here we have a kind of difference. We'll see in the implementation how we'll ensure that we have those counting for the inputs. Okay, but now let's see, we have 1 2 3 the combination for the inputs. Yeah. And for the outputs we can have what kind of combination? Depending, every output will be provided directly by the state. Okay, that means we'll have a more state machine. Yeah, and now we'll have 4 states: go north, wait north, meaning yellow, meaning north should stop to drive and do not initiate any traffic, just finish who is already in intersection, green. Yeah, this is meaning wait north. Go east, meaning red for the east, and wait east, meaning yellow for the east, red for the north. And seeing like this, this combination, we'll see that for the go north, we'll have the bit, the LSB will be in 1, and the MSB for the east will be in red. Yeah, this is red and this is green. Yeah. So now on detecting or staying here for 30 seconds. Yeah, for 30 seconds. So on no one request, or we will have request from 1 0 from the north, doesn't matter. We will have here, okay, staying here for the 30 milliseconds. Now the 30 second is finished. Now we are ready to get next state. Now if I don't have any request or nobody's asking, we are staying here. Or if north is still asking, we'll stay here. But in case if both are asking or east are asking for the intersection, we'll have the transition here. Now, and the transition and the yellow transition, yeah, yellow for the north, meaning stop driving, preparing for the changing to the green on east, means we'll what we will do? We'll switch on the yellow, the second bit, yeah, the second yellow for the north, and we'll still keep the red on the 5th bit, yeah, red for the east. We'll stay here for 5 seconds, and now look here, we have all the inputs here, all the combination. So that means we don't have any specific condition here. Anyway, it will change from the weight north to go east. Yeah, and same we'll see here, same, but vice versa for sensing. Now, when we will transfer this, I will prefer here, by the way, to make some combination or symbolic notation, but here we will keep still binary to have more related to what pin we are using. Yeah, so we have state go north, wait north, go east, wait east. We'll have request from nobody, request from both direction, request from the north, from the east, request from the north. Okay, nobody is asking, both are asking, north is asking, east is asking. Yeah, so we'll have here for the output the combination for the traffic lights. This is one traffic light and this is another traffic light. This is for the red, this is for the red, this is for the yellow. Yeah, and we have one traffic light, another traffic light. So we have this table that could be let's, and wait north always we are transferring to the go east, and wait east always transferring to the go north. Here we will transfer to the wait north only if we will have a request from the east, or only east is asking, or both are asking. We are going to the wait north, meaning go to the yellow. Same here. If we have if we'll have from the north asking, or both asking, we will go to the wait east. Yeah. Now converting from here to here, converting from here to here, we'll have the implementation. How we will have the implementation? By the way, let's make the attendancy. And after we will continue to let's see. Please be ready, because we have only a few minutes for that. So the key is this one, OIS6IY. We have 6. Okay. So, and give me the answer if you succeed or not to set it. Plus, just send a plus here. Others? Please, because we have to finish. Others, please. Okay. Again, few, and we will continue. Okay. Seems that everybody succeed. Yeah. And let's continue with the presentation. Now, let's see what we have here. Here we'll have the same, yeah, just a little bigger than we'll have pin mapping. So we'll define all the pin. We'll say that north pin is on the first bit, first pin of the Arduino. Yes pin, that means detection sensor, detectors, let's say some detector of proximity sensor, let's say like this, yeah, or some infrared detector, or depends. We have first two pins. After that, we will connect the traffic lights, the east traffic light on 3, 4, 5, and the north traffic light on 6, 7, 8. Okay, it could be configurable, but we can do like this. Now we have the states, and take care to be more countable. Why? Because we will use it here, and we should keep the counting, yeah, continuous. So now let's see what will be the state machine, and take a look here. It's the same, just the number of input we'll have here. Okay, for the LED we got 2. What it is? This is 2 because we have only 2 combination. For the traffic light we have 4. Now this is the table. The table is exactly what we have here that was converted from the state machine diagram. State machine diagram is converted to the table converted to the finite state machine configuration table. Yeah, it's the same. Now for the setup, we are setting the direction of the pin. Okay, initializing the first state will be go north. Go north is the 0. That means we'll have this combination. Okay, go north. And starting. Now going to the loop. Let's do first go to the loop. Now for the loop, we have output is equal to the finite state machine out. Okay, we are getting the out from the table. Okay, in case we have the state is go north is 0. It's selecting the 0. This is the output. Yeah, that means go north, red for the east, and green for the north. Yeah. So now set output. According to this, we are setting the output. Now, what is interesting, we have a different pin here, and we should see which of the bit is 1, yeah, and make a check, like create a mask here, comparing with out if this is 1, and set the state high or low. Now this value is applied to the specific bit. Same for the all order here until the 0. Yeah? 0 meaning 0 meaning green for the north. Yeah? And now collecting here, you see 0 is 1 green for the from here. Yeah, you'll have high from this combination, low, 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 and another high from here, because the 5th bit is 1 here and 0 bit is 1. Others are 0. So applied hit for the output. Now we are staying delay how much? We are staying here 10 millisecond for 3000. That means 3 seconds here. We have here 5 seconds. Yeah, and we are staying collecting it from here. Now input, get another input, get another input, collect the input. Now in case we have here some requests from the button or for the north pin or east pin, or in our case here we have a specific function that is collecting the input and providing the input combinations. So it will read the north pin and east pin, and now if this one is high and this one is high, return the binary high. Yeah? If this one is 1, then we set the bit for the north, the most significant, yeah, the north, this one. And if the east is here, and so on. So now we can see that we are getting the input, and it is helping us to collect according to the sensor the proper input to select the state. So this is just scaling. Even for the button, we can do something like this: the get input and set output. But for 1 bit, it's not the case, but better to do so. And in this case, this one will be as set output, and this will be a get input. Just if high, then return 0, and if low, if high, then return 1, if low, return 0. But this is I just did it. So now just for feedback, did you understand the idea or the implementation process of finite state machine diagram or design? From 0 to 5, please provide me some feedbacks. From 0 to 5, yeah, for all attendees. Others? Waiting, still waiting. So the idea is to follow those steps. First step, design the diagram, convert it to table, and this is related to this. Yeah, the outputs are related here, what we are generating. Here is the transition. Okay, first transition, second transition, and convert it to this table. Number of the input, number of the states, number of the outputs. Okay, same here. Convert this diagram to the table, convert it here. Number of the states, number of the inputs, and transitions. Okay, we have one transition, another transition, and all transitions are defined here. So this is similar. If we'll take a look at here, and here we have the same steps. The difference is here, okay, and of course on the initialization. So now the last problem, we can define the behavior of a follow line robot by defining that we have 2 sensors and 2 motors. And depending on which sensor we are detecting the line, we can drive one or another. And in the case we are going left or right, we are losing the line, and we are losing line here. That means we are going there, and lost here. What that means? Stop this motor and drive this motor. And what we have here, we have 3 states: going center, going left, turn right, center, left, right. The outputs, if we are in the center, we are driving both motors, and the number of the state is here. If we lose the motor on the left, if we have to drive the left, in this case we have 1, 0. If we have to drive to the right, we have 0, 1. Okay, depends. Depends how we are imagining. Drive to the left, to the right, or driving right motor. In this case, most probably we have here 1, 0, and that means 1, 0. In this case, we have to drive the left motor or drive the right motor, staying always 1 millisecond. Now, if we are in the center and both sensors on the detecting, in this case, drive center continuously. If we lose the sensor on the right, in this case, start the right motor. If we lose the sensor on the right, lose the sensor on the right, that means we have to start to the left, and vice versa. If we lose sensor differently, in the different case, we starting or stopping the one motor. In this case, losing sensor, that means we'll switch on or off one or another, in case we are in the center. Now, when we are on the left, we have different situation. Okay, if we are in the left and we have both sensors sensing, then turn to the center, switch the state to the sensor, to the center. And in the right, the same. When we have both sensor, that means we are on the line and go change state to the center. And same for the right and the left, and we have to change if we don't have the line. In this case, if it's left, keep left until you'll reach the line. If we are in the right and lost both sensor, go to the right. And here we have vice versa. Yeah, when it is on the left and we are driving left and still have a sensor on the vice versa. In this case, keep the center. This is vice versa, you see, and this is the same. Yeah, just this one is default. Yeah, and we will see that we have here one number more than in others. So let's continue. In this case, we will have something like this. Yeah, out, delay, next. We'll have the configuration, and of course, I didn't give an implementation because it will be the same: collect input and set output. So just copy paste and adapt the situation. So this is all what I wanted to discuss about the finite state machine. What is most important is that finite state machine is defining the behavior, and what we have to do to define the behavior by a state diagram, as we did here for an LED, here we did for a traffic light, and here even for a follow line machine. So when we are in the state that we have to define, are in a situation when we have to define the behavior, the best approach is to use finite state machine, meaning that we have states, different states, and we have in different states different actions or specific actions, and we have some we have to change between states by following some inputs. This is the general idea of the finite state machine. Everything else is just practice, practice, and practice. And of course, ask me for the feedbacks, but now at the end, I'm asking for general feedback regarding did you understand the general idea about how to use or what for we can use finite state machines? So please provide me the general feedback or put me a mark for this lecture. Waiting. Okay, thank you for your marks. Still waiting for others. Meanwhile, thank you for all for attending this class, and I'm expecting, for me, that was when I discovered this method to define behavior of the embedded system was a kind of, oh, I'm discovering the world, or I'm discovering what is the best solution, to not use if else, a lot of if else, just apply the formula and the principle of the converting from the diagram to table, and from the table a configuration in the source code, and everything will be fine. Once, if you'll try and if you'll solve one problem, after that you just will be an expert by trying different configuration table for the state machines. Okay, thank you for all, and see you. Thank you for all, and see you next time for the next type of control, and we'll have another two types of control: the fuzzy logic control and programming control, or pre-programming behavioral control. See you then. Thank you and goodbye.